All right, what's up? We are now working on the third problem. Let's go ahead and start up. The same steps as the previous problems on the first page. And if I see anything that's kind of weird, I'll point it out, and we'll work on it from there. So let's see here. Graphing out the equation. Put parentheses around the top and parentheses around the bottom. Let me make sure everything's in focus there. There we go. So parentheses 4x squared minus 2x plus 7 divided by parentheses x minus 3, and then graph it out. So here's how our graph's going to look. I don't really see anything up here in this region. And it looks like this is probably going to be a vertical asymptote here. I have a feeling that we're probably going to have a really, like a part of the graph that's going to be like, if this was the graph, it'd be like up here or something. Let's kind of see what we have, just graphing it by hand, and then work with the graphing calculator in a second. At least I know, kind of what the graph looks like over on this side. Let's try and make sense of all this stuff. So we could try to factor that top part, but let's see here. Numbers that multiply together to be 28 and add together to be -2. Yeah, those aren't going to happen. And in fact, you could even solve for zeros using quadratic formula in the top. So that's going to be pretty nice for the x-intercepts. That's going to be nothing for those. And, I guess you could kind of see that in the graph. There's like nothing that passes through the x-axis there. So, let's just go ahead and get all the other stuff. The domain, remember we just take the denominator since the top part doesn't factor. This is as simplified as our expression is going to get. So if x minus 3 cannot be equal to 0, then that means that our domain is that x cannot be positive 3. All right. Obviously, since this doesn't factor out of the top part, then there's not going to be a removable asymptote, so this is going to be our vertical asymptote. X is equal to positive 3. I can add that onto my graph if I want. Let's extend out the axes on this because I don't really like these little tiny graphing axes that we have. And if you want to borrow like a straight edge or something, a ruler in class, don't be afraid to ask if you just think that the graphing axes are just way too small. Most teachers have like a ton of rulers that they can lend out to you. Okay, there we go. So x equals 3, that's going to be our vertical asymptote. So 1, 2, 3, and then there's our little vertical asymptote. All right, very nice. Okay, horizontal asymptote. So to check the horizontal asymptotes, I look at the degrees of the numerator and denominator. The degree in the numerator is 2. The degree in the denominator is 1. Since the degree in the top is bigger than the degree in the bottom, we have no horizontal asymptotes. Then we check for the special case, which is the slant asymptotes. And since the degree in the top is 1 more than the degree in the bottom, then that means that we do have a slant asymptote. And that also means that we need to use synthetic division to find that slant asymptote. So the slant asymptotes are always linear equations, so we're always trying to break it down into just like 2 numbers with synthetic division, and that'll give us that slant asymptote. That's why it's always really important to make sure that the degrees are 1 apart, because when you divide it out, this degree takes away from this degree, and you're left with a degree 1 polynomial, in other words, a linear equation. So if we want to divide using synthetic division, we just take that, set it equal to 0, and we get our value 3, so 3 goes in the corner, and then we get 4x squared minus 2x plus 7. And just like what I was saying earlier on the first problem, with the slant asymptotes, we do not care about the remainder. So this box, we don't care what it is, we don't care what this is. We just care about these 2 numbers because that gives us our linear equation. So 3 times 4 is 12, 12 minus 2 is 10, so we get the equation 4x plus 10, so y equals 4x plus 10. Yikes. So this tells me with the slant asymptote, so yeah, that explains a bit for me because it tells me that there's going to be like a linear equation. Let me just even graph it out real quick. I'm going to graph out the slant asymptote, 4x plus 10. Okay, so here's our slant asymptote. So like if you pair that with the vertical asymptote, like those two are going to meet up like somewhere over here. And that means that our graph is going to be like way off of this. So I'm going to guess that the y values need to be like way higher than that. So I'm going to change up my window just to see what the graph looks like. Okay, so I'm going to make my y maximum something like 50. And I'm going to change my scale to 5 and see how the graph looks, if it even shows up all the way. So there's that lower part that we've seen. There's the upper part. All right, so now it is showing up. And look at how long it took for the graph to get that. Keep in mind that this top part is at 50. So yeah, geez, that's not going to even come close to fitting on here. You know, we'll try our best, I guess, and just kind of work from there. Yeah, this is kind of messed up. So y-intercept and holes. So there's no holes because we don't have any removable asymptotes because we can't even factor this part, so there are none on this. The y-intercepts, so the y-intercept is when we plug in 0 for x and see the y value. So if we plug in 0 into this expression, 0 minus 0 plus 7, so we get 7 in the top. And then 0 minus 3 is negative 3, so we get negative 7/3. That's like the first thing that we can actually graph other than the slant asymptote and the vertical asymptote. So 0, negative 7/3. That's even not really nice. That's negative 2.3 repeating. So 1, 2, 3. So it's like that coordinate right there. That's like the first point that we have. It's so messed up. All right, now let's take a look at the slant asymptote. So the slant asymptote is at 4x plus 10. So go up 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the slope is 4, so up 4, 1, 2, 3, 4 over 1. And down 4, so where was that? 14, 13, 12, 11, 10. So 1, 2, 3, 4, and then over 1. Okay, so here's our slant asymptote. Yeah, this is not really scaled very well, and it's just because of the gigantic numbers that we're working with here. But I mean, at least I can kind of, you know, graph this part out. This is a really messed up graph. This one goes basically along the contours of the asymptote, so it goes to here, and then it goes along this vertical asymptote here. The other graph, I'm gonna. Oh, what the heck, this might be kind of fun. I'll just keep going with the graph up here and try to graph it out, like higher up. Let me get some tape so I can keep this straight on here. Okay. My commitment to graphing is quite astounding. Here we go. Okay. And draw that line. We're gonna graph this out, dang it, if it kills me. Okay, so we keep going. So that's let's see here. Where would that intercept? At 3. So 3 times 4 is 12. 12 plus 10 is 22. So that was at 14, 15, 16, 17, 18, 19, 20, 21, 22. So that's basically where the graphs really will meet up, is somewhere like right over here. All right, so then let's keep going with the slant asymptote. I'll use my straight edge so I can make it real accurate, or try my best to make it as accurate as possible. There we go, that's a little bit better. And then the vertical asymptote, let's graph that one out too. There we go. All right. Okay, so let's graph a couple more points on here and see how this thing looks. Okay, so those are the only coordinates that they give us. So what we're going to do is get a couple of test coordinates in that region that's over here to the left, or to the right of x equals 3. So like we're going to plug in some numbers like 4 and 5 and 6 and see what we get from the table. So let's go to the table and find a couple of coordinates from there. So 4 gives us 63. Oh gosh. All right. So 4 is going to be at 63. We're up to 22. 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63. Okay, so at 4, it's at 63, so somewhere up here. And then at 5, it's 48.5, okay? So 48.5, so at 5, it'd be like over here-ish. I don't know. I'm kind of giving up on this one a little bit. I tried to stick with it, but you know what? It's just what happens sometimes. But then notice what happens when it gets a little bit larger. So at 5, it's there, and then at 6, it's a little bit lower. So like right over here maybe. And then 7, it starts to get a little bit larger, and then it starts following along the rest of this or the slant asymptote right over here. So the graph looks like this, basically. So it took me 2 sheets of paper, and maybe I can extend this out a little bit further here. So our graph basically looks like this, where we have the vertical asymptote, the slant asymptote, and then the graphs, the contour along the asymptote lines themselves. So yeah, pretty neat, right? You can guarantee without any uncertainty that like nothing like this will be on the test. This is just kind of like an exercise to find all of these values, but the graph, this is insane. Like, we wouldn't ask you to graph up to like 63 or anything like that. Maybe you get a couple test points from it, and then just kind of say like, yeah, hey, that's where it's going to be. We just want the general idea of the shape of the graph, kind of like the polynomials section that we had. But yeah, all right, maybe I went a little bit overboard on that problem, but you can write down a couple of other coordinates that you plugged in too, just kind of get an idea of how it looks. Okay, anyways, so blah, blah, blah. All right, now let's move on to the 4th problem.